Let us now look at three important ways that a function might be discontinuous. Take some pictorial examples. Here's our function. If you have a hole there, it already renders it discontinuous. There is a break in the curve. We have to jump from one location to another in a non-connected way. Now, call this A, and there's another facet here that even if we were to put a point, right, to find the function somewhere at A, just not at the hole, right? Unlike over here, where the function value had to be exactly the same to render it continuous. If we were to define the function somewhere other than the hole to exist, then this would still be discontinuous. So whether you have a dot somewhere above or below the hole is irrelevant. As long as there's a hole somewhere on this curve, it will be discontinuous at that location. But let's see why. Right now, if we take the limit as x approaches a from the left of this function, we will get the height of the hole, right? As x heads towards a from the left, certainly the function is heading towards the hole value. It's not heading towards the function value, right? It's heading towards the hole value. And let's just call that b again, just to have something to call it. So b. As x approaches a from the right, you have the same scenario. Also approaching b, right? As x approaches a from the right, the curve is moving down towards the hole value, again, not the function value. So therefore, overall, as we've seen before, the limit does exist, approaches a, of this function, and it is b. So therefore, the first condition is satisfied. The limit does exist. Okay? Now, if I call this height up here c, for instance, it doesn't really matter what I call it, as long as I don't call it b, because that would not be true, then it's pretty obvious that f of a also exists, right, and is c. Now, if there were no point here whatsoever, right, just the hole, and no point above or below, the function was not defined at a, then certainly it cannot be continuous, right? F of a would not exist at all. A function cannot be continuous where it is not. It doesn't really make any sense. But to make this case more subtle, I put this point here just to show that even if the limit should exist, and now also f of a exists and is the value c, but we see that the third condition fails because these two are not the same value, right? Even though both exist, the limiting value is not the same as the function value. So therefore discontinuous, and this is called a removable discontinuity. Removable because if I simply define the function in a very small way, just redefine it in a very small way. That is, if I defined f of a to actually be b instead of c, in a sense, the hole would then align with the point, and the curve would flow straight through here, making it continuous. So because it only takes a very small redefinition of the function to render it continuous at that location, it is called removable discontinuity in that case.